Morning, everyone. Thanks to the organizers for inviting me to give this talk, and especially for putting me as the first talk after the dinner, so there's less people to witness all the work that I should have done and didn't. So today I'm talking about a collaborative effort that I'm leading towards building a volume-limited sample of extremely low-mass white dwarfs. As the name suggests, these are white dwarfs with extremely low masses. How extremely low, however, is still somewhat of a subject of discussion. But for the purpose of this talk, I'm going to refer as extremely low mass white dwarfs, or ELMs, the ones with masses below 0.3 solar masses, and other helium core objects as low mass white dwarfs. So because of the way hydrostatic equilibrium works for white dwarfs, low mass implies a larger radius. So for the same temperature, an ELM is going to be larger and therefore brighter than a canonical mass white dwarf, as illustrated in this diagram here, where sizes are to scale. But what makes these objects interesting enough that there's a few talks dedicated to them in this conference is that they shouldn't exist. If stars self-isolated, but stars seem to be even worse than humans at doing that, so thanks to binary interaction, ELMs do exist. And because they are binary products, they are very useful for constraining this poorly understood evolutionary channel. The reason why they can only be explained by binary evolution is very simple. We know that main sequence lifetime scales with mass, and we know that our universe has a finite age. So if we simply plot this approximation to main sequence lifetime and compare it to the age of the universe, we see that only stars with masses above 0.88 solar masses have had enough time to evolve off the main sequence. And if we use an initial to final mass relation, this corresponds to a mass of 0.5 solar masses. So if we consider vanilla single stellar evolution, this is the minimum mass a white dwarf can have. In practice, this can be a bit lower, especially because there's a lot of things not taken into account by this approximation, in particular metallicity. But how much lower this can be is another subject of discussion. We've not only known about this limit for long, but we've also known for very long that there are white dwarfs below this mass limit. So this is the mass distribution that Bergeron and collaborators derived back in '92, when some people in this audience were probably even born yet. And back then we already knew that were white dwarfs with masses around 0.3, you can see it over here. And the authors already pointed out that nearly 10% of the stars in their sample required binary evolution to be formed. And shortly after that, there was some observational work to confirm that. So they observed 7 objects at the low mass end and found that 5 of them were indeed in binaries, which led to the conclusion that low mass white dwarfs need interaction to be formed. And this went unquestioned for quite a while until things got a bit complicated when there were observations of this cluster, NGC 6791. And it was found that the white dwarfs in this cluster, they are mostly low mass. You can see here the masses and the observed spectrum. And this cluster has a very low binarity rate, only 14%. So it's hard to explain this population as coming from binary evolution. So Kilic and collaborators suggested that instead mass loss was enhanced due to high metallicity rather than interaction, because this cluster is very metallic. This motivated them to have another look at the field population of low-mass white dwarfs, and they found that the binary fraction is actually only around 50%. So they suggested that this high metallicity mechanism was probably also happening in the field as well. But there's probably some mass below which you do need binary interaction, so they suggested that there should be a systematic search for binaries in this mass range here to determine what is, in fact, the binary fraction there. A lot of work was done by the ELM survey in this mass range. Warren is talking about this shortly, so I'm not going to spoil with any details. But in short, what they did was to follow up spectroscopically white dwarfs in the SDSS footprint whose color suggested that they had low masses. And once you have spectra, you can just fit it, see which ones have low masses, see which ones are binaries, and that's all very easy and done, right? No, unfortunately not. And Warren's already laughing because he knows it's not easy. This is fairly straightforward if you have a white dwarf that is hotter than around 10,000 Kelvin with a log G above 5.5. Below that, the parameters start overlapping with the main sequence, and that's where we have the so-called SDA problem. Because these objects have very similar spectra, they can be put into the SDA class, but you can't really tell from the log G and effective temperature alone if it's a white dwarf with a low mass or a metal poor main sequence star. This gets more complicated because below 10,000 Kelvin, the width of the lines is actually not very sensitive to log G. This is illustrated here, where at the top there's a canonical mass white dwarf for reference. This low gray here is a no main sequence star with a log G of 4. And down here we have a spectrum that fits a log G of 5, but at this temperature range, the uncertainty is around 1 dex. So based on the spectrum alone, we have no idea what this is. Before Gaia came along to give us radii, so we would be able to tell an ELM from a main sequence star, the solution to this was essentially to look for objects in closed binaries. Because for main sequence stars that have similar log G and effective temperature TLMs, the Roche criterion alone rules out periods shorter than around 9 hours. So if you have an SDA with an orbital period shorter than 9 hours, it cannot harbor a main sequence star, and it must be an ELM. But if we rely on binarity to identify our ELMs, we are not going to find that binary fraction that Mokremin was asking us about 15 years ago. And on top of that, we don't expect all ELMs to necessarily be in closed binaries. There are two main channels to form ELMs. One of them is the common envelope channel, which we heard a lot about yesterday. We know all of the uncertainties, but still it should form closed binaries. But there is another channel, which is a stable Roche-Loeber flow, and this channel can form longer period ELMs. And if we are selecting objects based on short periods, of course we are going to favor the common envelope channel. This was nicely demonstrated by Lee and collaborators with population synthesis. So this is their mass distribution, and in green we have objects coming from common envelope evolution, in red from stable Roche-Loeber flow. And if we select only the hotter ones that we can identify from spectra and the ones with short periods, this is what happens. Stable Roche-Loeber flow systems are basically gone, and we are only looking at common envelope channel systems. So this is our status before Gaia. We had around 150 objects known, selected mainly using colors. Binarity was often used as a criterion, and the periods observed were up to 36 hours. On the other hand, theory not only predicts that longer period objects can exist, but actually even single stars are possible. Only because you need interaction to form an ELM doesn't necessarily mean that you're still going to observe it in a binary. So for example, if you have a common envelope with a planet that doesn't survive the common envelope, you're going to see a single star. And the predicted periods are up to 100 days. So I'm comparing observations and theory. Doesn't mean theory is right. It could be that this is not correct. But the best way to get better models, in my experience, is showing that the current ones don't work. So we definitely need more observations. So thankfully, Gaia came along, which means we don't need to rely on binarity anymore to identify ELMs. We can rely on the fact that they are more luminous than the canonical white dwarfs. So this is an absolute magnitude versus color diagram. In here, I plotted as the colored symbols non-ELMs. In red, if the parallax is bad. In blue, if it's good. And in green here is a model that results in an ELM with a mass of 0.32 solar masses. And based on this, I defined these cuts in here in blue to select a sample of ELM candidates. I also applied some quality cuts, starting, for example, with a parallax better than 3 sigma. And then I cross-matched this with SDSS and noticed that this 3 sigma cut actually doesn't work. In here, for example, in yellow are stars that have F-type in SDSS spectra, and so there's a lot of contamination if we use only a 3 sigma cut in parallax. So if I increase this to 5 sigma and tweak this red border a bit, the contamination gets down to around 10%, so that's what I did. And there's around 12,000 objects that pass this cut. But in this region here, it's not only ELMs, it also contains canonical white dwarfs with M companions. So the next step was to do some color cleaning to separate the sample. So for example, I used W1 minus W2, and here the colored symbols are in red CVs and in blue detached white dwarf and dwarf binaries. And you can see that they typically have W1 minus W2 larger than 0. You can see the 2 peaks in the distribution here. So I just selected the ones on the other side. And doing this color cleaning, I ended up with just short of 6,000 ELM candidates, shown here color-coded by parallax over error. You might be wondering why I'm talking about the DR2 selection when DR3 is already out. Not to worry, I'm going to show you what happens with DR3. So this diagram here is showing in red the DR2 selection, and in blue how they look like in DR3. So the main thing to notice is that there are loads of objects that move to below the selection, so they turn out to be canonical white dwarfs. This is probably just because these are the faintest ones in the sample, so it's very easy to have inaccurate parallaxes over there. But what if we were to do a catalog fully based on DR3? This is something I'm still working on, but I'm going to show you some preliminary numbers. So the color magnitude cut and quality cut results in around 18,000 objects, so it's a 60% gain compared to DR2. And if we do the color cleaning, we have around 10,000 candidates. So the numbers increased by around 75%, which I think is similar to what was the increase in the white dwarf catalog. The gain is mostly below 17 magnitude and especially around 19. But DR3 has more than just improved parallaxes. It also has many new tables that we can explore, some of them containing even binary information. So when DR3 was out, I was very much looking forward, especially to 2 tables. One is called the two-body orbit that contains objects with two-body solutions coming from either astrometry, spectroscopy, or time series photometry. And the other one is called acceleration table, and it contains proper motions that show an acceleration, so this could suggest that they are very long period binaries with a period that is longer than the Gaia baseline. So I readily cross-matched my DR3 and my DR2 candidates with this, and I got nothing. It was very disappointing, but perhaps not too surprising. For comparison, for the hot subdwarf catalog that has over 40,000 objects, half of which we expect to be in binaries, there were only 30 objects in these tables. And hot subdwarfs are much brighter than ELMs. So maybe we just have to wait longer until our systems are solved as to two-body orbits. DR3 also has the BPRP spectrum. And here the cross-match was a bit more fruitful. 14% of the sample have BPRP spectrum. And one of the nicest things about the spectra is that you can derive other magnitudes. For example, you can look at SDSS magnitudes, which we are more used to. And that's one of the things I did. So this is a magnitude, absolute magnitude color diagram using SDSS-G and G-R. And then we can compare, for example, with the ELM survey selection, which is this box over here. And you see that's more or less encompassed by my selection. I go a bit hotter, where I'll admit it's mostly junk that I'm getting here, because this is where reddening will play a significant role. So I have canonical objects that I reddened and end up in my selection. But here in the cooler end is where I expect to find the more interesting things. And of course, this is an all-sky catalog, and it's going a bit deeper. So I also have more objects. I have, for example, 400 in this box, and I think the ELM survey has less than 100. But of course, this is our only candidate, so it's probably I still have some junk in there. We also have epoch photometry in Gaia DR3. 172 of my stars were classified as variables. There's a few that are probably contaminants in my sample because they were classified as Delta Scuti or Aurora. They are mostly up here. There are almost 50 that were classified as pulsating white dwarfs. Those are the blue dots, but they are everywhere. So instead of being like an instability strip, so I don't really trust this classification, but they are probably indeed variable. I just have to look at them and see what they actually are. But of course, DR3 was only out earlier this year. I wasn't sitting idly by doing nothing, waiting for it. In the meantime, I was working on a volume-limited sample built from DR2 and following up this sample. So the sample is shown as black dots here. There are around 400 objects. The green crosses here are known ELMs for comparison. And as I showed before in the DR2, DR3 comparison, there was a lot of contamination at the bottom here of objects with inaccurate parallaxes. So I've been working on a refined sample that uses this solid line instead of the dashed line. The sample is all sky, and it goes down to magnitudes around 20. Our collaboration got a fair amount of time to follow up these objects. For the brighter ones, we've been using INT and SOLAR. For the fainter ones, Gemini, VLT, and the GTC. And our approach has been to take at least 2 spectra per target, so we can not only confirm them as ELMs and obtain the atmospheric parameters, but also probe for binarity. There were initially only 7 known objects in our sample and a few tens with SDSS or Lamotte spectra, and we have followed up 250 so far. So the sample is around 72% complete, as illustrated here. Completeness, unsurprisingly, goes down for fainter magnitudes. For objects brighter than 18, we are 83% complete. And for a sample of 150 parsec, we are almost complete. There is only 1 object that hasn't been observed so far. The analysis for the full sample is still ongoing, so I'm just going to show you some preliminary results for this 150 parsec sample that contains 16 objects, 15 of which have been observed. Those are the ones in blue here. There were 5 known objects in the sample. All of them are ELMs, or at least low mass, and all of them enclose binaries. 2 are in the literature as canonical white dwarfs. One of them is a double degenerate system, and that's why it appears overluminous. And the other one has no binarity information, but so far it's just a canonical white dwarf. There is one, there is a low mass one that is published as single, but we took a second spectra that shows a radial velocity shift, so we cannot rule out that it is a binary. And there's also new systems. For those, I'm going to show the spectrum up here with the best chi-square model shown in red. This is still a preliminary fit, but it gives us a good idea. So this first one has parameters very well consistent in an ELM. We only have 1 spectrum so far, but the radial velocity is quite high, so it's probably a binary. This other one also shows an RV shift. The fit is not particularly good, especially because this one has a lot of reddening. So here the light gray is before reddening and extinction correction, and the dark gray is the corrected one. This one is a very interesting one because the log G is very low. It actually hits the border of our grid, but it does show a radial velocity shift, so it's probably indeed an ELM. And this is one if we only looked at the spectrum, we would probably have missed it because it does have a very low log G. These other 2, they are probably more low mass than extremely low mass, but both of them showed radial velocity shifts. And finally, there's 2 right at the edge of the selection that turned out to have F-type spectra. Interestingly, both of them are excluded from the selection in EDR3 and also DR3. So using the new parallaxes does improve the selection. And finally, there's just one that hasn't been observed, but this one is scheduled for GTC, so hopefully the sample will be complete soon. So just summarizing these results, there's around 70% of the 150 parsec sample that turned out to be extreme low mass, or at least low mass. 6 of those were known, 5 new, and 8 out of these 11 seem to be are either known close binaries or have high radial velocity changes. So it does seem that short period systems are more common. We still haven't found a clear one coming from stable Roche laboratory. And the binary fraction, at least from this sample, seems to be at least 70%. So indeed, quite high, as one would expect. But of course, it's still all low number statistics, so yeah, stay tuned for the results for the full sample. And yeah, just to summarize, DR2 revealed thousands of ELM candidates. DR3 shows even more candidates. There's not a lot of helpful stuff in the additional tables, but hopefully in the future there will be. And the follow-up of the volume-limited sample is nearly complete. Please stay tuned for the results. Thank you very much.
Hey, Ingrid. The Gaia tables that you looked at, that's astrometric accelerations. Mm-hmm. And unless there's long period systems, you probably wouldn't expect any. Like if you have short periods of a day or something.
So yeah, they will be very long periods. For the hot subdwarfs is the ones with periods of 100 days or so.
And is that already maybe telling you that there aren't that many, that long periods are unlikely?
Yes, I think so, yeah.
And the other quick question I have is, some of them have very, very high mass functions, and there was some speculation whether the primary is a white dwarf, or could it be neutron star or something else in some cases? In some of the published ELMs.
In some of the published ELMs, you mean? I didn't quite hear that. Can you say that again?
Oh, like the estimated mass of the primary is sometimes very high. Mm-hmm. And are they all definitely white dwarfs, or could it be something more exotic as a primary?
In which sample?
Any.
Oh, you mean the mass of the unseen companion? Yes. Is quite high. Yeah. I don't think there's anywhere we could say for sure it's not a white dwarf. I think it's likely more white dwarfs, but I guess Karim wants to comment on that.
Yeah, I can just comment on that. I mean, we did look at several binaries using Chandra and Radium. We didn't see anything in any of those. So it's, at least in those, yeah, it's you know, it must be white dwarfs. So you showed one object with log G4, and like really like 7,000 degrees or something.
Yeah.
I mean, what is that exactly?
So from the radial velocity shift, it's probably an ELM, or at least a pre-ELM, but where it is in the HR diagram is, it seems like it's already cooling, so it's a bit of a weird one. I haven't looked at what DR3 does to it, so maybe it moves up here and it is a pre-ELM. Yeah.
So first of all, for the neutron stars, right? There are lots of millisecond pulsars that have optically identified.
Yeah, that's a good point. Yeah.
Right. I want to ask you about the period distribution. So it definitely seems like you're mostly finding short periods, but what's the longest period that has a secure RV curve? And like, do you think there is a long period population?
So there is one pre-LM that has a period of, I think, 200 days. Paper is Voss and collaborators, I think 2018, but as far as I know, that's the only one that has a very long period. Usually they are found amongst the hot subdwarfs, because for the hot subdwarfs we do have a large population of long periods. So we find them, we see that they are actually below the helium burning, and then they must be pre-LMs. But looking for ELMs or pre-LMs, we haven't found many that are long periods, or maybe even none.
Oh, thanks.
Just curious, Ingrid, have a reddening cut or a latitude cut in your sample?
A latitude?
Reddening or a latitude?
No, I don't have a reddening cut, but for the DR3 sample, I'm definitely going to do that, because that was one of the main issues, is just I have some very hot white dwarfs that are red and just end up in my sample, yeah. I need to update my apps, but that can wait.
Thanks, Ingrid. This is great. Do you have any objects that you have found that have SDSS photometry and were not observed in the ELM survey?
I haven't checked that, but probably not. Yeah. Yeah.
Yeah. Hi, Ingrid. In that log G4 object you were just showing.
Yeah. If I can bring it back up again. There you go.
Where's that calcium line coming from?
Yeah, there's a calcium line. Those are fairly common in ELMs. We do see them very often. That's an interplay between, like, rotation can make metals float. Yeah.
Thanks.
Hi, Ingrid. So how much have you looked into finding periodicities for your new RV shift systems with other time series photometric surveys?
So I cross-matched with ZTF and Catalina and I think Atlas as well. So the ones that are in there, or at least were in the public data, I know the periods. But I think very few from the 350 parsec sample had periods in these surveys.
And were you able to detect a period for them, or nothing?
For a few, yes.
Okay.
I don't have the numbers at the top of my mind, but there's quite a few that do have periods, yeah.
Any more questions? I just had a general comment as someone that works more on the theory side, and probably this is my fault for not being more, looking up all the papers I should be looking up. But I find, in terms of comparing the observational results with say the binary population synthesis, it helps me to have certain parameters in tables and papers, right? So, for example, like having the masses, that's usually something that if you can have that value, obviously that's included. But also indications of composition, right? From an observational perspective, usually these white dwarfs are categorized as DA, DB, or other types of white dwarfs. Whereas in theory, when we say helium white dwarf, we mean something different, right? We mean the white dwarf is primarily composed of just helium. So just consolidating this, how the language, from the observational side, and then how we actually think about it from the theoretical side is something that, well, I should probably work more on, but maybe as a community we can try to communicate these things a little more effectively.
I'll keep that in mind for when I finally publish this.
Cool. All right, we have time for one last quick question. If not, let's thank Ingrid.